This session we've collected, not all, but a bunch of the big heads that are here. And, you know, BJoy is a big head, and there's a whole bunch of big-headed people. I mean, these guys are smarter than the rest of us. They can read hard books. They can see patterns that we can't see. They're extraordinary. It's like a different race. They're amazing. I don't know how to talk to this guy. I say, you live in Aspen, huh? And I don't know what else to say next. And he's such a big-headed guy. This is how big-headed a guy he is. Twice I told him, you should look at this book I did because you'll find it interesting. He went out and bought one because he never opened his fucking bag. I mean, it's a big-headed guy. BJoy.
That's one of the more unusual introductions I've had. Well, it's a pleasure to be here on a panel with such distinguished other speakers, or in a session, rather, with other distinguished speakers and in front of a distinguished audience. I was one of the founders of Sun and designed computer hardware and software. So I know something about technology. I also know something about design. I don't know much about entertainment. So if you find me entertaining, that'll be my contribution. But we stand here at the beginning of a new century that I think is going to be an incredible century, a very different century than the 20th century, because we're at a point where we're having a confluence of information science and the physical sciences, which is making all sorts of incredible new things possible. I think Ray Kurzweil will probably talk about some of these new possibilities. He's talked about them in his very interesting new book. But I think it's quite likely, for example, that the 21st century will be a century of abundances rather than a century of scarcities because of these new technologies. What I do in computer software affects this because it's largely the ability to control the manipulation of matter and genetic material and physical materials with software, the ability to use computers to put together large databases that can manipulate the materials that make these kinds of new abundances possible. So it's likely to be a very exciting century. I think we have an opportunity, for example, in the 21st century to alleviate material poverty. It won't be difficult. We should have enough material abundance that we can do that. But I think a challenge then, if we start thinking about doing things like that, is to go beyond just alleviating poor people's material poverty, but also think about how do we make their lives worthwhile? How do we give them education in their lives and give them challenges and worthwhile things to do? And that's going to involve a lot of change. So it's, I think, going to be a very exciting 100 years. I hope to be around for a substantial part of it, as hopefully many of you will also. Now, in understanding what's going to happen in the 21st century, I think it's important to think about what's going to be common, easy to get a hold of, and what's not. We all feel a lot of time pressure in our lives. Clearly, time is something that we're going to have a deficit of. And maybe material goods, for example, computers should be very inexpensive. Most computers in the 21st century are made out of single chips or even smaller things, so they will cost almost nothing. We can have as many of them probably as we want, but then we'll have to deal with all of them. And spending the time to deal with all of them will not necessarily be, something is free, we have a lot of it, and something we have very little of, we get to spend all our time managing this other thing. That's not necessarily a very good trade-off. So what I've been thinking about a lot for the last 20 years is how can we build systems that are more reliable, and how can we have computers and organize our computing and our software in such a way that they don't drive us completely crazy. And this is not an easy problem. And you have to ask yourself, for example, why are the things so fragile? And I spent a lot of money putting a central sort of stereo system, an automated stereo system in my house, and it's just a complete joke, really, because the honest truth is if you walk up and you go to push a button, a lot of times nothing happens. because one of its many parts is malfunctioning. Some relay is stuck in one direction or other, or some wire has come loose, or some power has failed on some box. As we add more and more complexity to these systems, they fail in more and more frustrating ways. And I feel like a repairman for my own house. But there's something going on here, and as we put more and more software into things, because everything is becoming networked, all of our devices are becoming more and more networked. As software and microprocessors get cheaper, we're putting software and networking in almost everything. And as these things then start to work together, they can fail in all sorts of incredibly spectacularly frustrating ways. Now, some people would say, you can point to the personal computer and say how frustrating that is. And it's certainly the case that monopolies don't tend to produce good products. And that explains part of the reason why personal computers are so frustrating. But I actually think it goes beyond that, and that there's something actually intrinsically hard about doing software. I was in one of the conversations yesterday. I think software is very fuzzy. The users can't quite tell you what they want. And so it's kind of fuzzy in that way. And inside the machine, it's a place where you have to do all this, create all this kind of invisible stuff. It's not easy to write great software. There are a few people in the world who are great at it. And in fact, I've heard of stories now in Silicon Valley where startup companies are giving up to $1 million cash bonus for the key engineers, key programmers to join a startup company, which is unprecedented. Fortunately, it seems to be capped by some IRS rule about the deductibility of compensation up to above $1 million. So maybe it'll hold there for a while. But it's quite clear that this is very, very hard. Writing good software is very hard to do. Software is becoming more and more a part of our environment. The entertainment kind of stuff we do, the way in which we design things like, here's what appears to be a piano, but there's probably more complexity in its software than there is in the rest of the device. So doing software well and doing software that's reliable and isn't constantly frustrating us is going to be a big challenge. So 20 years ago, when I was at Berkeley, and I was working on an operating system called Unix at the time, and it was driving me crazy because I lived in married student housing down in Albany, and every time the machine would crash, I'd have to drive back into the campus and reboot the machine. So I started fixing the system so it wouldn't crash so often, kind of improving the mechanical reliability of the system. And that's a very, very rewarding thing. It does make the systems more reliable. But what you quickly find out is that the systems are not simply mechanical. Once you take a network, a computer network, and you put systems together and they start interacting in funny ways, you can't predict the behavior of the collection of machines and the way they interact from the behavior of the individual machines. They create kind of nonlinear, complex behavior. They start interacting in very, very strange ways. So we've been working for the last decade or so to try to figure out how can we design software for networks that behaves in a more rational, predictable way. We started off by saying, if we can come up with a programming language which is very well defined, then we can say very precisely what our software does. And so as we spread it around the network, it'll mean the same thing everywhere. And we showed the first public demonstration of the Java language was here at a conference in Monterey, probably in '94 or '95. And that's been quite successful. And the whole idea was programs should mean something. And you'd think that that would have been something that software engineers would have had on their side. You know, if you're a mechanical engineer, the laws of physics exist. And so you have some idea what the rules are about your mechanical device. But in software, when people would write a program, if you put the program on different computers, the program would mean different things. And that's a very, very frustrating thing if you're trying to build something that's reliable and something that wants to move around the net. Something that wants to run on devices that haven't been invented yet. You want to know what the rules are when you get there. You can't test your software on a device which hasn't been built yet, but if you put a website up, it may be browsed by sites that haven't been, browsed by machines that haven't been built yet. So that was quite successful. That improved this kind of mechanical reliability. But we also saw coming this whole sort of nomadic phase that we're entering now, where everybody has a cell phone, and a cell phone very quickly can become a personal communicator, your PC, and as you wander around, it encounters different environments. your desktop computer sits there. It always has a keyboard and a mouse. It's always kind of in the same context. It's sitting in your office. It's next to your printer. But as you wander around and with your personal communicator as your device that's being aware of your environment, it gets much more difficult. What software is appropriate to run in this situation right now? What things can I do right now? Well, you can, if the device can see what's around you, it can make a suggestion. It can look at the capabilities that are in your environment, things you might want to do. I'm in an airport, you know, I want to be paged before my flight leaves. Or it can know that you like jazz music and you're in a room and you can push the button that says play jazz and can look out and find some way of playing the jazz music, maybe on this piano, maybe on a stereo, but not at the level of I have to push this button, aux input here, all this kind of stuff that drives everybody crazy. So we tried with this technology called Genie then to say if we went out into the world and we categorized what things were out there, kind of made a taxonomy of what objects are out there, and then as your device, if you walk into a room with your pocket device, your device can look out and see there's a printer here, there's a piano, and all these other things. They can recognize them because they've been given names in a hierarchy, much like the kind of hierarchy we'd make of the plant and animal kingdom, and can thereby figure out what it's possible for you to do. And that's achieved some limited success. But I still think that despite that, it's still too frustrating. It's still too frustrating to imagine that we're not going to go kind of crazy when we have thousands of devices out there. So what we've been trying to do is think about the ways in which we could essentially civilize this environment where we're going to have a lot more devices. The first thing is, where am I? If I have my pocket device, it knows where it is. It can know what kind of context it's in, like your pocket device can know that you're in a meeting and know not to ring if it's a cell phone. So that is really a form of common sense. So no one would accuse a desktop computer of having any common sense. But it's something that you're probably going to want in your portable device. How do you represent common sense? It's not an easy thing. In fact, it's not really a Boolean thing. It's not really a true-false kind of thing, in that if you ask your desktop computer a question twice, you probably expect to get the same answer. But let me give you an example of when you ask say I ask my pocket communicator, where should I have dinner tonight? And it knows where I am. It knows what kind of restaurants are around. And it simply picks the best restaurant. But every time I ask it, it picks the best restaurant. So every time it picks the same restaurant. Well, that is by definition wrong because it's boring. Okay? So you immediately get the sensation that something different is going on here when we have mobility injected into the equation and we start putting together people's preferences and common sense in this way. It's not going to be the simple kind of true-false kind of stuff that we see in the desktop machines. So this is going to be a big challenge. For most of us, the way in which we act with our electronic environment is going to come through these devices that are always with us. And yet the ways in which we've done software, the ways in which we've organized the kind of computing we do on the desktop really don't apply to the styles of interaction we expect to have with these pocket devices. So we need an enormous amount of new design to make that work really well. Now, one thing that we noticed about 10 years ago, actually after John Gage and I were traveling, we were in Paris, and we just went into a bookstore and we picked up this book by Jacques Attali. It was called Ligne Horizon. It was a book it's called Horizon Line. John just decided he would translate it from French to English just to brush up his French, but we found this chapter in this book about a nomadic man. It was a wonderful chapter, described about how miniaturized electronics was going to free us from location we could just wander around. And we started thinking about this and realized that, well, personal computers had been the same for a very long time. Basically, you have a screen, a keyboard, and a mouse. In the future, there were going to be multiple modalities, multiple ways of interacting with the device. And in fact, I think the demonstration here at TED of Java was probably a demonstration of what was called MovieWood. It was what we would, at the time, would have called the far web, which is that you sit on your couch and you have interactive entertainment, kind of what the holy grail for the set-top box. And so we decided very early on in the 90s that sitting up at your keyboard and sitting back on your couch were going to be different. Wayne Rosen used to call them near and far. And then we had this idea of the here web, which is the one that's with you all the time, and that's going to be very different, that the kind of information, the way you want to organize things for something that's always with you versus something that's near or far, could be as different as a newspaper is different from a newscast. Even if you're looking at the same kind of information, you're in the same environment of stimulus, it's going to be presented to you in a very, very different way. So we had the idea that there would be a near web, a far web, a here web, and also what I guess I would call a weird web, which almost rhymes with near, far, and here. But basically, just you can talk to it, and this is something that Ray's worked on, the idea of voice recognition. You just put microphones in your clothing, and you don't need to be holding something or sitting up or holding a remote control. You can just kind of talk to your clothes. Now, in order for that to work, to have a microprocessor in your clothes, you probably need washable ICs and a few other things, and batteries in your shirts, and there's a lot of room for value add in the clothing industry. But that doesn't seem that far out with the kind of technologies that we'll have as we move towards pervasive computing in the 21st century here. So what I'm working on now is this whole notion that we're going to be able to have lots of computers. Computers are going to be very free. If I'm running a service on the web and I don't quite have enough compute power, I just call up and say, send me another 1,000 processors, and they'll just show up in a box. Let's sort of stick them on the shelf or on the rack or plug them in somehow. We can have an enormous number of disks and processors, but we don't have, what we do have is a very limited amount of time to manage these things. So the question is, what sort of style could we use to create an environment where we can be very, very flexible about the numbers of machines we have and the way they're organized, so I can just throw in another processors and it can sort of just automatically kind of do the right thing. What we find is with mechanical systems, they're relatively inflexible. If things are bolted together in a very precise way, and I want to stick another one in, I got to re-engineer everything. And that's the way most systems work today. They have databases and lists and configurations and tables and funny IP addresses. And so this very mechanical engineered kind of nature of our systems really makes them kind of inflexible of these kinds of changes. People at the Santa Fe Institute and other places have been looking at an idea of using more of a biological metaphor, where you use models from biology in the natural world to suggest that you can make the systems more flexible, and you can waste, if you had 1,000 processors, maybe you only use half of them, but you can use half of them in a sane way, so you don't have to try to manage every single last one very, very precisely like you would do in a mechanical system. But even that may not be enough. I think the thing I notice is, getting back to this notion of the brittleness, is the reason the systems are brittle is that, like you have an account at Yahoo, and if you go to Yahoo and an entry in one of their files has got deleted, you no longer have your account. A hacker gets in and just cracks the file. You may be the founder of the company's best friend, but you won't be able to get in because it's all organized into a central database, and there's just an entry in that database. The fact that you know people doesn't get you anywhere. So there's this wonderful idea, kind of the 6 degrees of separation idea, which is the idea that what if you organize systems not around databases and lists and passwords, but you organize the system around the relationship between things. So if I'm here at the conference and I can't get in, I have to find somebody I know who knows somebody who's powerful enough to let me in the door. The kind of networking that we do in our personal lives. That tends to make things much more robust than having everything in a list, and I'm not in a list, I can't get in. But that's not the way anybody builds computer systems today. They're all organized in this very, very mechanical, plugged together kind of rigid style. And so I've been thinking a lot about using these small world graphs. But we clearly need to do something. If the processors are going to be, and the memory and all these things that we can use to make the systems more reliable and more powerful are going to be very, very inexpensive, and we can have a lot of them, but we can't afford to manage them, we have to find some new organizing paradigm. So we still struggle, even after 25 years of trying to make the systems more reliable, in some sense to deal with this incredible abundance. Because incredible abundance, while it's an opportunity, also presents us with this enormous challenge. So I guess my message is that we're heading for an era of incredible abundance with some incredible challenges, opportunities to do really great things, really improve people's lives, and there's lots of great work ahead for designers and engineers and technologists. Thank you.